Hello everyone. Today we are going to see the classification of the reactors. So, the reactors are classified according to the fuel used, the neutron energy, the moderator material used, then the coolant used, or the purpose of the reactor, and the homogeneous and the heterogeneous fuel and moderator combination. So, we will see the classification of reactors and then we will see the typical reactors. So, let's start. So, the classification of reactors, here the first point is including the fuel. So, depending on the type of fuel, the reactors are classified. When the natural uranium is used, the reactor is called as a natural uranium reactor, and the abundance of the uranium-235 is very less. And when the enrichment of the uranium that can be done, then the reactor is known as enriched uranium reactor with uranium-235 content nearly equal to 3.5%, or the reactor which contains the plutonium-239 as a fuel, then the reactor is also called as a enriched uranium reactor, or the uranium-233 reactor. So, simply dependent of the fuel like uranium-235, then the enrichment of the uranium, then the reactor is called as enriched uranium reactor. So, here the fuels are uranium-233, uranium-235 and the plutonium-239. So, these are the fuels for the reactors, and depending on that the reactors are named. So, here is the reaction which is given for the generation of the plutonium. So, from the uranium-238, when we bombard the neutron, this neutron get captured by the uranium-238 nuclei. So, this capture is called as a resonance capture, and from this uranium-239 will be generated. This uranium-239 is with the excess energy, and it undergoes beta minus decay in 2.35 minutes, and there is a formation of neptunium-239. And after 2.35 days, this neptunium-239 will undergo decay, and there is a formation of plutonium-239. So, this is the first step or the first reaction which occurs in the formation of the plutonium-239, and this is a substitute to uranium-235 as a fuel. Then another reaction is also given. So, as we have told, the plutonium-239, uranium-233 and the uranium-235, all these are used as a fuel for the reactors. So, we have seen how plutonium is generated. Now, we will see how uranium-233 is produced. So, we have to take initially the thorium nuclei. Here, the isotope's mass is 232. When we bombard neutron, again it undergoes the resonance capture reaction, and there is a formation of thorium-233. Then this thorium-233 will undergo the beta minus decay in 2.3 minutes, and after that there is a formation of Pa-239, and after 27 days there is a beta minus decay, and there is a generation of the uranium-233. So, uranium-235, plutonium-239 and the uranium-233, all these three are the fuels for the nuclear reactors. Now, we will see the next point. Dependent upon the neutron energy, the reactors are classified. So, here the neutrons are of the higher energy, intermediate energy and the lower energy. So, higher energy neutrons are called as the fast neutrons. The intermediate energy neutrons and the last one is a thermal neutrons, or this can be called as a slow neutrons. So, The reactors are called as a fast neutron reactor, intermediate neutron reactor, or the slow neutron reactor, or the thermal reactors. Then there is a next classification that is based on the moderator substance used. So in the reactors, the moderators are graphite, heavy water, or the light water, and less often the beryllium is also used in the moderator reactors. So depending upon this moderator material like the graphite, heavy water, or the light water, so the reactors are classified based on this. And the moderator materials are the materials which are useful for the conversion of the fast neutron into the slow neutrons. And the fourth type is coolant use. So this reactors are be classified on the basis of the coolant material that is used. So as air, water, or the light water, liquid metal like sodium that are used as a coolants, or the that are used for keeping the reactor cool or for the extraction of energy. So this moderator material or the coolant material are very helpful for the nuclear reactors because they reduces the chances of explosion and they controls the overheating. So we will see the next point. So based on the purpose of the reactor, the reactors are classified. So as we know, the reactors are used for the power generation. Then as we know, there is a very less abundance of the uranium-235 as a fuel. So we have to find out the substitute for that uranium-235. So we have to prepare the plutonium, and that can be used as a nuclear fuel also. So the plutonium extraction, this is also one purpose of the nuclear reactor. Then we have to produce the different isotopes. So isotope production is another purpose. They are not purely research reactors. So these are the purposes, and depending on that the reactors are classified. The last one is a homogeneous or the heterogeneous reactors. So depending on the whether fuel or the moderator are in one phase, or they are present in the solution state, or they are present in the different phases. So they are be classified as a homogeneous and the heterogeneous. So as we have seen here, the classification of reactor that can be done on the basis of the fuel, then neutron energy, moderator used, coolant material used, the purpose of the nuclear reactor, and the homogeneous and the heterogeneous reactors. So here is a simply combination of the fuel and moderator material. They are in one phase or in the different phase. So this is the classification. Now we will see the typical reactors. So we will discuss the relevant issues in designing the nuclear reactor using different fuel moderator combination. So for the designing the nuclear reactor, we have to consider the fuel and moderator combination. So a quantity which is referred to design the nuclear reactor, and that design parameter is capital F. And thus design parameter capital F is defined as it is a ratio of number of moderator atoms and the number of fuel atoms. So F is equal to number of moderator atoms divided by number of fuel atoms, and that F is extremely important in designing a nuclear reactor with K is greater than or equal to 1. Now we will see the first type here. The natural uranium, ordinary water, or the graphite reactor. So as we have seen, the typical reactors, or when we want to prepare or design any kind of the nuclear reactor, we have to keep in mind the fuel material and the moderator combination. So simply depending on that, the first reactor is natural uranium, ordinary water, or the graphite reactor. So here natural uranium is a fuel, and the ordinary water or the graphite, that are the moderator materials. So as we know, uranium-235, its abundance is very less. It is nearly equal to 0.72%. And there can be no self-sustaining fission chain reaction with the light water as the moderator. So simply when we use uranium-235 as a fuel and the ordinary water or the light water that can be used as a moderator, at that time there is a no self-sustaining fission chain reaction occurs with the light water. So the maximum value of the reproduction factor K, so this K is a reproduction factor and that value is maximum and it is 0.8 at F is equal to 5. Means when the fission or the design parameter, this F, it is equal to 5, the K value or the reproduction factor, that will be is equal to 0.8. So when we use the light water or the ordinary water as a moderator, the value of the reproduction factor is maximum, which is equal to 0.8. And when the F value is higher, that is equal to 400, that will be observed when we use the graphite moderator. So design parameter is higher for the graphite and that will be 400. So this value of the resonance escape factor P in this type of the reactor. So the K value is 0.8, F value is 5 when we use the light water. Then we use the graphite as a moderator, F is equal to 400 and that value is of a resonance escape factor P in this type of the reactors. So we will see the next classification of the reactor based on the fuel and the moderator combination. And here is natural uranium, heavy water, homogeneous reactor. So simply the fuel is a natural uranium and the heavy water, that is a D2O, and the fuel and the moderator materials are in the same phase. So here the heading is given homogeneous reactor. So natural uranium, heavy water, homogeneous reactor. So simply the D2O is the moderator and the reproduction factor K is greater than 1 and F is varied, that is a design parameter or the ratio of the moderator atoms to the fuel atoms, that will be changing, it's varying, and the K rises to 0.02 to 1 or it will be greater than 1. So when F is equal to 1 to 1.17, F will be 300 to 400 for the natural uranium heavy water nuclear reactor, and the reactor is homogeneous in phase because the fuel and moderator are in one phase. Then we will see the C point or the third kind of the classification based on the fuel and the moderator combination, and that is enriched uranium graphite reactor. So here the fuel is a enriched uranium and moderator is a graphite reactor. So uranium adequately enriched nearly equal to 3.5% in the isotope uranium-235, and it is possible to make a reactor go critical, that is K is very greater than 1. So when reactor goes to a critical state, when K value is greater than or equal to 1. So F will be 400 for the graphite moderator reactor, and that K value or the reproduction value rises with the degree of enrichment in the uranium-235 fuel. So simply enrichment means just we have to adequately enrich the uranium-235 and nearly equal to 3.5% enrichment can be done in the isotope of the uranium-235, and the reactor may undergo the critical condition and K will be greater than or equal to 1. F value will also increase and it is equal to 400 when we use the graphite as a moderator. Now we will see the next point. Natural uranium homogeneous reactors. Natural uranium heterogeneous reactors. So here is a heterogeneous. We have already seen the natural uranium heavy water homogeneous reactor. Now we will see the natural uranium heterogeneous reactors. So main difficulty with the natural uranium homogeneous reactor except with heavy water is the high resonance capture loss. So when we use the natural uranium as a fuel and the heavy water or the deuterated water that can be used as a moderator, there is one difficulty or the disadvantage. Here the high resonance capture loss will occur. So uranium is placed in the form of a well separated rods in a matrix of the moderator. So that fuel material or the uranium material that can be taken in a rods in a matrix of the moderator, and the ratio of the surface area to volume of the fuel element that will be greatly reduced, and hence also the loss of neutron by resonance capture that can be reduced. So here natural uranium heterogeneous reactor, here what is a fuel? It is a natural uranium and the moderator is the heavy water, and here maximum loss of the neutrons is due to the high resonance capture loss. So that we have to keep that fuel in the matrix of the moderator material so that the loss will be reduced. Now we will see here the required conditions for the natural uranium heterogeneous reactors. So first is the optimum fuel rod diameter. So we have to reduce the loss of the neutrons in the natural uranium heterogeneous reactor due to the resonance capture. So that here the 3 to 4 steps are given. So we will see that steps. First is the optimum fuel rod diameter. So increasing the rod diameter, the resonance capture loss and hence and increase of the factor P. So as we are going to increase the rod diameter, the resonance capture loss and the increase of the factor P, and on increasing rod diameter that will reduces the thermal utilization factor, and the rod diameter should roughly correspond to 1 mean free path of a thermal neutron in uranium, and the mean free path of a thermal neutron that will be calculated by equation lambda is equal to in a bracket n into sigma T bracket is to -1. So here n is a number of fuel atoms and it is equal to 0.048 into 10 raised to 24 atoms of uranium 238 per centimeter cube, and sigma T is the total absorption cross section for the fast neutrons, and that is 7.2 into 10 raised to -24. When we put all these two values of n and sigma T in the equation of the lambda, we will get the value 2.89 centimeter. So that lambda or a mean free path of a thermal neutron, that is 2.89 centimeter. Now we will see the second step, optimum interfuel rod separation or slowing down length. So the interfuel rod separation should be such that a fast or slightly slowed neutrons leaving the surface of one fuel rod gets fully thermalized before reaching the surface of the next fuel rod. So we have to fast neutrons and we have to convert that fast neutrons into the slow neutrons or the thermal neutrons. So slowed down neutrons leaving the surface of one fuel rod that will get fully thermalized before reaching the surface of the next fuel rod. And this slowing down length has been found to be 5.3, 11.2, 19.1 centimeter in water and D2O, that is a heavy water. Also the carbon is used as a moderator and here it is a graphite. So third is a approximate valence sheet of the reactor. So in a natural uranium graphite heterogeneous reactor, the production of neutron is around 2.52 per uranium-235 fission. So as we know, around 3 neutrons will be generated in one fission of the uranium-235. 2 to 3 neutrons will be generated. Exactly its value is given, it is 2.52 per uranium-235 fission, the neutrons are produced. So for the uranium-235, when there is a thermal fission, 2.46 neutron will be produced, and from the fast fission of a uranium-238, there is a formation of only 0.06 thermal neutrons. So the resonance capture by uranium-238, that will be 0.8, then the radiative capture by uranium-238, it is 0.2, then the absorption by graphite, it is 0.3, then the absorption by other materials, it is given not 0.05, then the loss by leakage, it is 0.09, and the chain propagation, that is a K, it is 1.08. So total value of the neutron addition, that is a 2.52. So from one fission 2.52 neutrons will be produced. And next step is a pressurized heavy water reactor. This is also called as a PHWR. So here deuterium is used as a moderator and the primary coolant with the natural uranium fuel bundles in a horizontal candria, permitting on power withdrawal and refueling. So simply, in the pressurized heavy water reactor or in the PHWR reactor, the heavy water is used as a moderator and the primary coolant, and the natural uranium is act as a fuel. So here the fuel bundles in a horizontal candria are taken and permitting on a power withdrawal and refueling. And a typical 235 megawatt PHWR has a 3672 fuel bundles in the candria, and each of 15.2 kg of the natural uranium or the uranyl oxalate as a ceramic pellets encased in the zirca alloy tubes. And the calendrias are the high pressure reactor vessel holding the fuel. So simply in the pressurized heavy water reactor, deuterium or the deuterated water is act as a moderator. Then the natural uranium is act as a fuel. So here the fuel bundles are taken and they are kept horizontally in a calendria and permitting a power withdrawal and refueling. And here around 2